So, good afternoon, everybody. Welcome to the online course on high pressure physics. Coming to lecture will be on simulations. So, the first question before we starting, let us see regarding the experiment. We have learned how to generate high pressure using various kind of pressure cells like large volume press, diamond anvil cell, and we have also learned how to achieve extreme high pressure, how to do high pressure, low temperature experiment, and what are the different kind of experiment that can be done like X-ray diffraction, using X-ray, using optical like Raman scattering, infrared. So we know that when how to generate the pressure, how to do the measurement, but the difficulty in those experiment is it's not always possible to interpret data unambiguously, and also there are several things which can't be deduced from experiment. Like if you want to know what is the mechanism of transformation under pressure, so we need to know what is the atomic level, what is happening during this transition, and then it provides a much more insight into the kind of phenomena we are interested in. With the help of simulations, we can study various phenomena like structural stability of various systems with the pressure, where one can investigate vibrational property, one can deduce phonon dispersion relation, phonon density of state, one can also compute the vibrational entropy of the system, and one can compute the electronic structure of the system, like electronic band structure, how the charge density varies when you apply a pressure, and how the charge transfer take place from one atom to other. And recently, this simulation technique has reached to a level where one can do a simulation which is quite intensive in terms of a computer, and one can do the structural prediction like based on the only the knowledge of the composition at particular pressure or temperature condition, what will be the stable structure. That kind of simulation is also possible. So from experiment we certainly get several informations, but certain like atomic mechanism, it is not easily deduced from the experiment. So this simulation provides a better insight into the kind of phenomena that is taking place at high pressure. So broadly, if you classify these simulation methods, one can categorize in two parts. One is the classical molecular dynamics or classical method, and another one is the quantum mechanical solving the Schrodinger equation. One can do the first principle calculation, and in that also there are large number of different methods available. One can do the all electron calculation, pseudo potential based calculation, and there are so many. So in today's lecture, what we will be learning is how to do this classical molecular dynamics simulation. And in the coming lecture, we will see what is the advantage of first principle calculation, how to perform these first principle calculation, and what are the different quantities or physical properties that can be computed using a first principle simulation. So today's lecture will be we will be focusing only on classical part. So here is the outline of this talk. First, we will give a brief introduction. I already mentioned some of the point. Then we will learn what is the classical molecular dynamics. In case of classical molecular dynamics, what is the basically phase space, relevance of phase space, and time average. And then ergodic hypothesis comes. Then we need to solve the Newton's equation of motion. In particular, we will say Verlet algorithm. There are various kind of these various variety of these algorithms, and the most important part is interatomic potential, force field. And to do these simulations, we need to apply periodic boundary condition. We need to use various basically thermostat or barostat, depending upon kind of a simulation we are interested in. If we want to do microcanonical or canonical or isobaric or isothermal calculations. And then we will see how what are the steps involved in performing these simulations. And in the end, I will give one example that when you do this simulation, what kind of result one gets and how these results uh, helps in interpreting the experimental data. So as I already mentioned, when we do experiment, we can do the X-ray diffraction. We get diffraction peaks, which again indicative of a structure of that material, and this peak basically is characteristic of atomic arrangement in the system. And when we apply the pressure, this this diffraction pattern changes. But the thing is, it's not always possible to deduce these structure at high pressure using a limited access of this Q range in the diffraction experiment. So if you can do the simulation and try to find the structure, the stable structure, and then that can help in determining the structure at high pressure. Basically, these simulations help in interpreting the experimental result. Similarly, if you do the Raman scattering experiment, certainly when you apply the pressure, there will be changes, and those changes are again related to the change happening in the system. But the interpretation is non-trivial. In this case also, these simulations help in interpreting these data, and we will see in the example how these simulation can be utilized to interpret these data. So as I mentioned, there are two type of calculation. One can do the classical molecular dynamics simulation or first principle based simulations. Both has advantage and disadvantage. If we talk about the classical molecular dynamics, this is particularly relevant for amorphous system or liquid system where the number of particle is large, because we need to simulate large number of particles to simulate this system, and it's very difficult to simulate these system using a quantum mechanical calculation, yeah, or you can say the DFT based calculation, because the computational power required is very high. So if one is interested in studying the high pressure melting of material, then this classical molecular dynamics simulation is really very helpful. If one wants to investigate atomistically what is happening in the alloys, where you have, let's say, one component fraction is very small, then to simulate those systems, one need to use large or very large cell, and the total number of atoms will be very large. So in that case, these quantum calculations is very computer intensive. So in that case, classical calculations are really helpful. The main disadvantage or the difficulty in doing reliable classical molecular dynamics simulation is the force field. So we will come to it. How we do the basically classical molecular dynamics simulation, what are the various things that are involved in this simulation, and what is the role of this force field and potential. And then maybe we can discuss why it's very important to have a good force field or potential. So based on these simulations, we can calculate various kind of physical property, macroscopic physical properties. So basically, if you see this simulation is, if you see in terms of relation between statistical mechanics and thermodynamics. So statistical mechanics is a microscopic theory of system, and from this statistical mechanics one can deduce the thermodynamic parameters. Similarly, this classical molecular dynamics also deals with the you can say microscopic systems, and from these simulation one can deduce the thermodynamic quantities like thermal extension, density at desired pressure. So one can determine the equation of state. One can do what calculate the bulk modulus, vibrational properties, specific heat. And this is particularly for amorphous or liquid, or you can say alloy system. Because if your system is like instead of alloy, it's a single element or few element system, then one can deal this system with the higher accuracy using the quantum mechanical calculations. So, what is classical molecular dynamics? So, MD simulation is a computer simulation technique that models the time evolution of atomic or molecular system based on the atomic force field. In this case, in these simulations, these atom or ion particular particles are dealt explicitly. Particle interacts via relatively simple analytical potential function. So that's why these calculations are less computer intensive, though certainly it also requires higher computation power. Means these calculation is not possible to do on a what बंद हो गया
What happened? Some technical hitch?
Yeah, system got shut down or something.
Okay.
The presentation is not visible.
No, I can see, but
I'm not able to see.
okay.
The PPT is not visible.
Okay.
Put Alt tab. So in this case, basically these particles interact via relatively simple analytical potential, and then we need to solve these Newton's equation of motion. Those are integrated for all the particles simultaneously. If these equation, if we try to solve analytically for a large number of atoms, it's almost impossible but if we want to if we are doing with the computer, it's relatively simple. So with the molecular dynamics, one can simulate almost 10 raised to power 6 number of particles depending upon the model and also the computational resources, and one can simulate the system to a large time scale, 10 picosecond to 1 microsecond, and also people are done up to millisecond. As I already mentioned, these calculations are less expensive compared to quantum mechanical calculation. one can do a large system, one can study, and in case of classical molecular dynamics, it's easier to include temperature and pressure. We can study the effect of pressure on the system easily at a elevated temperature also. That's why one can study the melting at high pressure using these classical molecular dynamics simulations. And certainly these simulations help in interpreting the experimental data, which can provide alternative interpretation to the phenomena. And this also can be used to test the theories of intra or intramolecular interaction that is taking place. And one can obtain detailed molecular level information. As I already mentioned, what is happening during structural transition, how this structural transition is taking place, based on the structural transition mechanism, one can reduce the transition pressure if we know the path, if particular kind of stress that is involved, and if we apply that stress, non-hydrostatic stresses that can reduce the structural transition pressure, etc. So when we are simulating n number of atoms in a system, so we have 6n values that defines the state of the system, and there are 3n coordinate and 3n momenta. And each combination of these coordinate and momenta define a point in the 6n dimensional phase space. So what we are doing is basically we are following the system in a 6n dimensional space with time. So you have a one point at a particular time that represents the system. When as the time evolves, this point moves in this phase space, and we are following the trajectory of the system in the phase space, and that is used for calculating various physical quantity. But what is the relation between this time average and ensemble average? So as I mentioned, in MD simulation, we are doing simulation with the time, and most of the time we are doing basically calculating the physical property by taking a time average. But in actual, these quantities are basically ensemble average at particular point of time. So here the ergodic hypothesis comes into the picture, which says that ensemble average is equivalent to the time average. So we can directly use these MD simulations to calculate the physical quantity. So of course, one need to do the simulation for a sufficiently long time scale, so that this average quantity, whatever we are interested, comes out to be an you can say is accurate. Depending upon the kind of simulation, one can do this simulation in canonical or other ensemble, and we will come to it that with the incorporation of various kind of temperature and pressure thermostat, we can do other simulation also. So what is the steps that is involved in the classical molecular dynamics simulation is basically, as I already mentioned, we are following trajectory of all the particles in system as a function of time, and we can calculate the trajectory average property using the by taking the average over the time. Now, what we want is basically we want to see how the system evolves with the time. For that, what we have to do is we can solve the Hamilton's equation of motion. Basically, if you see Newton's equation of motion, Hamiltonian equation of motion, these are equivalent, but provides a slightly different picture. So if you are doing working in a Cartesian system, then Newton's equation works well. But if one wants to work in a generalized coordinate system, then not only the generalized coordinate system, but if there are constant of motion, then this Hamiltonian equation of motion provides an advantage. So since in this simulation we are working mostly in the Cartesian system, so we are using basically solving the Newton's equation of motion, and there are various algorithms for solving this equation. And let's take an example of a simplest Worlet algorithm. So what is being done is basically if you take the time evolution of any position Ri and you expand it in a Taylor series about a known point in time that is t0, what you see is basically you can expand in a various term at time t is equal to 0, then derivative, difference, and then double derivative, and so on and so forth. So what you can do is if we can look into this slightly at a different time scale before t0 and after t0. Let's take this position of this Ri as time t0 plus delta t and t0 minus delta t and do a Taylor series expansion, and then we add it together, then we get this expression. When we rearrange this expression, we got this equation. So this equation, what is important to note here is we want to calculate the position of all the particle at time t0 plus delta t. So which is function of current position Ri at t0, previous position Ri t0 minus delta t, and acceleration, and of course time step that we have chosen. So this equation, using this equation, one can basically evaluate the position of all the particle with time. There are large number of algorithm possible. So if instead of basically expanding position, one can as well expand the, sorry, I think if one can expand this velocity also in the Taylor series. So in that case, what we get is basically velocity Worlet algorithm. So in this case, so when you expand this velocity in a Taylor series, and when you do the various combination of resulting expression can be used to determine the next position, velocity, and acceleration of the particle. So if you do these various combination, one get a different kind of algorithm to integrate the equation of motion, like leapfrog, velocity Worlet, Riemann, etc. In all these algorithm, what is being done is higher order terms are truncated. So in the simulation, what is done is basically all these gray are the stored position. So what you have is basically you have a position at time t, you have a position at time t minus delta t, and acceleration at t minus delta t. So what is being done is, depending upon the position, only position of the atoms, one calculates the acceleration. So this acceleration is calculated through Newton's second law. And in all the algorithm, you see that first this acceleration is calculated using Newton's second law, F is equal to ma, or you can say the potential, average potential from all the atoms decide what will be the acceleration. And because of due to this acceleration, then one takes acceleration, position, previous position, one can reduce the next position, and then so one can repeat this process to get next step, position, acceleration, etc. In this normal Worlet, this velocity is not calculated explicitly. So if one wants to do constant temperature simulation, then one need to evaluate these velocities. So this provides basically one computationally one extra step is involved in this one. So in case of leapfrog, what is being done is in velocity is calculated at intermediate time step. So you start with the position, all the position of atoms. So the position of atoms decide the what will be the average potential, and that potential, from that potential one can deduce what will be the force, and that force one can deduce acceleration. So, and using this acceleration and the velocity, one again calculate the new velocity, and then from velocity and position one calculate the next position. So that's how this simulation move forward. Likewise, if one uses velocity wormlet, then these all the quantity at particular time are used to basically generate the next position. And then, as you see, and always for calculation of acceleration, one uses potential. So from the and that input is only the position of the atom, and you can construct this way. I think I missed the slide slightly. So when we are basically solving Newton's equation of motion, I mentioned that from the current position we use a previous position and current expression, we can predict next upcoming position at time increment delta t in future. And what we require is basically we require a potential, and potential is only function of the position, and simply by dividing by a mass one can reduce the force and one can reduce the acceleration. Okay, as you know that forces are themselves the negative gradient of potential V, hence the needed for a potential function, and frequently this is referred to as a force field. And trajectory are the step-by-step records of all the particle position coordinate along the time interval considered. Now the important thing is the time step. So if we take a higher time step, we can simulate for the longer time, but there is a difficulty. If we take higher time step, then there is a possibility that your simulation due to the integration, it becomes unstable. So generally what is being done is basically your time step should be almost 1/10 of the highest frequency of your highest frequency that present in your system. So there are ways by which one can slightly increase the time scale. But we are not going to do this detail, and that is particularly important when one deals with the heterogeneous or soft materials. Now comes the interatomic potential. As I mentioned, in case of classical molecular dynamics, it's very important to have a good interatomic potential, because that is the supplied in case of this simulation, and if it is accurate, then only it will produce a good result. So you can say the important part or bottleneck in this simulation is the force field. So it's not always possible to basically generate a potential which will work in all the conditions, or you can say from starting from very low density to very high density. So it is important to test this potential before doing a detailed simulation. And as I mentioned, that these calculations is the potential depends only on the nuclear position. So this electron, if there is a contribution from electron, that is basically ignored. So if one wants to see the effect of electronic redistribution in the system, then certainly one need to do quantum mechanical calculations. And there are various kind of potentials possible in the you can say the pairwise potential or two body, three body, and the important thing is these potentials would represent your system accurately. So if you see the general form of this potential is basically you have a bonded term and then you have a angle term. So basically if there is a change, it depends upon the change in the bond length. If there is a deviation from equilibrium bond length, then the energy changes. Similarly, this gives the restriction on the angle. Then you have a dihedral angle, which is basically torsion and rotation of a 4 atom about central atom. Then you have a non-bonded potential. So if you have a van der Waals or electrostatic potential, so this complete form is known as a force field, and in case of classical mechanics, this is basically parameterized. So you have an analytical form of this potential, and it is very easy to compute. Once you know the accurate form of the potential, it's very easy to calculate these forces. But in case of quantum mechanical calculation, this calculation of this potential itself is very time consuming. And if you will see in the coming lecture that when you are doing quantum mechanical simulations, the difference, the main difference is basically the calculation of the potential. In those calculations, also these atoms or ions are treated classically. Only thing is that potential is calculated through quantum mechanical calculations. So, as I already mentioned, one need to supply a parametric form of bond potential, angle potential, or dihedral or improper. So this depends upon your system. So in this, most of the time, this bond potential works. But if your system is molecular, then one need to supply some these other potential so that you can clearly represent your molecular system. So this is a simplified force field or potential. If you have two ions sitting, two atoms at a particular distance, then when you change the distance, there are two interactions. One is the attractive that varies at 1 by r raised to power 6, and then there is a repulsive term. This is because of the dipolar interaction, and this is because of exclusion. So effectively, you have this potential. Now you can use this potential in a simple way and then do the simulation. In practice, the finding this potential is very difficult, and finding accurate potential is very difficult. That's why people do quantum mechanical simulations when one is interested in a more accurate result in a small system. The another important thing in this classical simulation is basically periodic boundary condition. So what we are doing is we are simulating only a small number of atoms in a simulation cell. But in reality, our bulk system has almost Avogadro number of atoms or molecule, that is 10 to the power 23, and that is not possible to simulate. So what is being done is basically what you use is basically periodic boundary condition. Why? Because if we use a small cell, and if you take an example that if you have a small cube of 10 by 10 molecule, and then you can see the almost half of the molecules are on the surface. So this won't give a true picture of the bulk properties. So what is being done is basically one apply a periodic boundary condition. In this, what is done is basically you take a small simulation cell, and then what you do is basically if the particle leaves from box from one side is replaced by an image particle that is entered from the other side, or you can say these particles are rigidly connected. So if this particle moves this way, then the other particle you move this way. So move inside the cell. So thereby you can basically apply this in all these directions. It's a periodic boundary condition, and then you can remove the effect or you can say surface effect, and the system will be considered as a bulk. Of course, there will be some effect of these simulation cell size if there is a, and this simulation cell is small, then there is a possibility of interacting these nearby atoms. So that's why it's always good to take as big as possible the unit cell, so that this periodic boundary condition doesn't give artifact. And of course, you require these boundary condition in case of award sum. Then what is award sum is basically you are calculating a long range electrostatic energy. So one need to use large number of atoms, or you can say long range. In that case, this periodic boundary condition helps. And how it is being done is up to certain distance, these Coulomb energy term is calculated in real space, and after that distance, it is calculated in reciprocal space. So therewise, it basically reduces the computational time. Now comes to the thermostat. Like if we want to do any simulation at particular temperature, then one need to use thermostat. So okay, so what is being done is basically we need to modify these Newton's and scheme with the okay. Before I will get what is how we define the temperature. Temperature is defined by the basically velocity of an individual particle. If we take an average of this one, that gives the temperature. What we want is we want to keep temperature constant. For that, one uses various kind of thermostat. So the starting velocity of the system, one can take as a Maxwell Boltzmann distribution. Then that defines the temperature of that simulation cell. When you allow your system to evolve, then these velocities changes, and that leads to the change in the temperature. So what is being done is one can rescale all the velocity according to the Maxwell Boltzmann distribution and keep the temperature same. And in the simulation, what is done, you start with the basically some initial distribution, and then you adjust all the velocity in such a way that at particular time the temperature follows this. The basically velocities are scaled in a way so that this is equivalent to your defined temperature. Here, so this is the temperature, which is calculated from the instantaneous velocity in the simulation cell. And then what is being done is basically to reach a target temperature, one scales the velocity by this equation, and then this one can keep the temperature of that simulation at particular instant of time. So there are various kind of thermostat which has basically advantage in one or other systems. So one can use the velocity rescaling, which is not very good. One uses a nausea over. So we are not going into the detail of these various thermostats. Now we will come to the pressure or barostat. So if one wants to simulate a system at high pressure, so first we need to know what is the how we define the pressure in a simulation cell. So this relation gives the pressure. So what is the this is pressure is equal to nkt by v plus 1 by 3 v, and this is the basically force summation Ri dot Fi. This is the virial, and where F is the force on individual atom at a particular position. So based on the force, if one take average of all these forces, and then that gives contribution to the pressure. But how to manipulate this pressure? Similar to temperature, here the pressure, if you take a case of Barentson barostat, what is being done is what you do is basically you can scale the length, or you can say R, in such a way that your pressure, your system reaches to a desired pressure. This regulation gives the pressure from the calculated from at instantaneous time from all the all atomic position and force acting on those atoms, and then one can scale these length scale with the factor, which this factor is given by this relation. So when you scale these length using this factor with some rise time Tp, one achieve a desired pressure. You can see in this figure, when you start this barostate at a particular time with different rise time, one can see that this pressure, when your rise time is higher, the pressure uh, increases slowly. You have a very short rise time, then this pressure increases very rapidly. So one can use this barostate to increase or decrease the pressure in your simulation set. When you are doing the simulation, what are the steps that is involved on during the MD simulation is basically first you select what is the interaction model, what is the interatomic potentials, that is a very important thing. Then one select what is the boundary condition. If we are doing a pulse system, then one need to use a periodic boundary condition. If you are interested in the surface property, then one can use only two-dimensional periodic boundary condition in 2 dimension. Then one need to put initial condition like what will be the structure. If you are simulating the crystalline system, then you need to supply the position, and if you are doing this simulation at particular temperature, then one can give the velocity according to the Maxwell-Boltzmann distribution, and then one can select which kind of simulation we are interested in, canonical, macro canonical, or isobaric, isothermal. Then if we are interested in uh, pressure temperature calculation, then these various kind of barostate, thermostat can be used to define the temperature of that ensemble. And then there are various kind of basically Newton's equation integration is possible. So depending upon the memory requirement and system and accuracy, one selects the particular algorithm, and then one does a basically simulation until one reaches the equilibrium in a various quantities, and then one can do detailed calculation, or you can say the simulation for a long time. And once this simulation is done for a long time, then these basically this trajectory in the phase space can be used to calculate the thermodynamic average of particular quantity where we are interested in, or you can say in terms of the slope, you can say you set up all the condition and calculate force from the particle position, then you solve the Newton's equation, and then this is how this it is done in a computer, and this is repeated until your desired time is achieved. There are various packages. Some of them are DL poly, GULP, LAM, PPS that can be used to do this simulation for high pressure. Mostly these packages are meant for biological systems, but one can certainly use these for system like condensed matter system as well. Now, what I will give is when you do the simulation, how this simulation can help in interpreting your experimental data. So we take an example of crystallite aluminum phosphate. So with this these simulations, how what information we can extract is how this transition is taking place, how the coordination of particular atom changes with the pressure, what will be the pressure volume behavior. When you increase the pressure, whether it's monotonous or it changes, that one can simulate. And of course, one can interpret the data. So this is one simulation where we have done on aluminum phosphate, what you see is when you basically when you increase the pressure and allow it for some time, then you can clearly see that there will be a change in the coordination of these atoms. So when you start this one, these are 4 coordinated, and with time, when you apply the pressure, this system relaxes and this uh, aluminum becomes 6 coordinated. So you can clearly see that these atoms comes closer, and then the nearby oxygen also forms a bond with the 2 nearby aluminum atoms. If you can see from other direction that when these these aluminum atoms comes closer and then new bonds are formed. So with this simulation, we can see how the coordination of aluminum changes with the pressure. So when you do this simulation, you can also compute how the various lattice parameter changes with the pressure. Then that can be compared with the experimental lattice parameter, and of course one can reduce the pressure volume behavior. So this is the pressure increasing cycle. When you increase the pressure, its volume decreases, then there is a certain at certain pressure there is a change in the coordination of aluminum that you see from the earlier uh, picture, that due to the coordination change there will be a sudden drop in the volume, and then this volume again monotonously decreases. When you release the pressure, there is a hysteresis in the PV behavior, which again clearly shows this is a first order nature of the phase transition. One can calculate various quantities, like how the radial distribution of different atom changes, and this also can be used. Like if you can clearly see with the simulation at a different pressure, there is no change in the radial distribution. Means the phosphorus, whatever is there in the initial starting pressure, it remains in the same configuration. But if you see the aluminum, it's you can say it's a coordination clearly changes with the pressure. Here you can say at 13 GPa you start getting an extra peak. So the radial distribution suggests that again this oxygen, some oxygen is coming closer and new bonds are formed. So this also can be used to interpret that with the pressure aluminum coordination also increases. One can compute the X-ray diffraction pattern, and then those can be compared with the experimental data. Thank you very much.
No questions.
You can start.